Minasan, konnichiwa, Zamurai Engineer this. It's still part 1, but this is what almost an introduction to the next part. We are going to name it Module 0A, Structural Steel Design topic. However, we will give you the template. Okay, it is now a template on how we would discuss the steel design. So this is developed by Scott Sibyan of University of Massachusetts, Amherst. So teaching modules for steel instruction. So compression member design. So what do you mean by compression member or column? So this is the representation of compression member. When we are talking of compression member, the structural element that comes to mind is column. So a column will look like this, and this is the what? As you can see, this is W beam, which is being applied as a column. This is W beam. This is the flange, the opposite flange, and this is what? This is the web. Okay. So it is a structural member subjected to axial load. So that is a column. So we'll take a look at the different pictures. We will do this particular example throughout the semester. So a 4-story office building with the pictures, photos, and discussion. So we will use the work of Sibyan from the University of Massachusetts. Okay, so we'll show this to you, and take note. It's very important. This is used for computation. Very important. Please take note of this. Screenshot it if you like. Okay, this is on the code NSCP, AISC. This is being used. Okay, P is equal to 0.9 for compression. So different value of P for different application. For example, tension, different values. Okay, for beam application, different values. So now we are talking of compression, steel compression, application for column. P is equal to 0.9. Take note. And this formula is PU is less than or equal to PN times P. Everything is P. So P sub N, right? Right? Is our target or design. This is our what? Design stress or design force. So P meaning force. In civil engineering, P represent force. So this is in terms of Newton or kilonewton. So as you can see, ASD, I will explain to the next module what do you mean by ASD. Okay, so axial strength, strength limit states, meaning we need to have what, some sort of allowance, so that we limit the states on the strength of the material, for example. So strength design, squash load, global buckling, and local buckling. We will look into this because we are talking of compression. So axial strength. Okay. So these are the differences of global buckling, local buckling, and another local buckling. So it depends on the direction. So here we have global buckling because we are having the deformities all throughout from the top to bottom. So global. So the orientation of the W flange, of the W beam, of the W type steel structure is like this. Then it will look like this. Okay, okay, the same, but it will just bend globally. Okay? Global buckling. Okay? How about local flange buckling? So flange, this is the flange, this is another flange, the opposite one. So local buckling is localized in some particular portion or area of the element. So the plants may deform like this. So in here, there is no deformation actually on the shape of the W type. Here, we have a noticeable deformation. Okay? So how about the local web buckling? Okay? So we have the web, which is the one who will buckle. So take a look. The web will deform like this. So there is a curvature. There is a deformity on the web alone. Compare it to the local flange buckling, the flange deform. So here, the web deform. That's why it is called local flange buckling, local web buckling. Okay? So we will also take a look at the video of the case study, the particular application that we will deal with here. So I will show you. So the failure modes, the different failure modes, just like global buckling, local buckling, and so on.